There is a star out there that should not exist. It burns with a light so strange, so extreme, that for decades scientists assumed it was simply impossible. And when they finally found one, confirmed, real, undeniable, it forced them to rewrite the rules of how stars are born and how they die. The question is, what exactly is this star? And why does its existence shake everything we thought we understood about the universe? Our galaxy alone holds somewhere between 100 billion and 400 billion stars. That number is so large it stops meaning anything. So think of it this way. If you counted one star per second, without sleeping, without stopping, it would take over 3,000 years just to count the stars in the Milky Way. And yet, for all that variety, giant blue supergiants, dim red dwarfs, ancient white cinders drifting through the dark, most stars follow the same basic rules. They ignite from collapsing gas clouds, they burn hydrogen, they die in ways roughly predicted by their mass. Most stars follow the rules, this one does not. In recent years, astronomers scanning the sky with increasingly sensitive instruments stumbled onto something that did not fit any clean category. A stellar object with a magnetic field so powerful it defies conventional models. A surface temperature pushing limits that theory said were unreachable for its size. And a rotation so rapid it should, by the physics we know, tear itself apart. They called this class of object an ultra-long-period magnetar, or, depending on the specific object, a magnetar-pulsar hybrid unlike anything in the known catalogue. Let that sink in for a moment. In a universe 13.8 billion years old, packed with hundreds of billions of galaxies, each holding hundreds of billions of stars, this type of object is so rare that we have only confirmed a handful of candidates. Ever. What makes it so special? To answer that, we need to go back to the beginning, to what happens when the most massive stars in the universe run out of fuel. Picture a star 20, 30, maybe 50 times the mass of our Sun. It has been burning for millions of years, which sounds like a long time, but compared to our Sun's 10 billion-year lifespan, it is a blink. These monsters burn hot and fast, and then they die violently. When the fuel runs out, the core collapses in less than a second. 1 second. The outer layers bounce off this collapsing core and explode outward in a supernova, one of the most energetic events in the entire universe. For a brief moment, a single dying star outshines an entire galaxy. What is left behind is a neutron star, a ball of matter so dense that a teaspoon of it would weigh around 1 billion tons on Earth, the entire mass of something larger than our Sun compressed into a sphere roughly 20 kilometers across. That is smaller than most cities. Now, some neutron stars spin hundreds of times per second. Some have magnetic fields 1 trillion times stronger than Earth's. We call those magnetars, and if you stood on the surface of a magnetar, which you absolutely cannot for reasons we are about to get to, that magnetic field would rip the iron right out of your blood before you got anywhere near it. But here is what no one expected. Scientists found a magnetar that pulses not hundreds of times per second, but once every few minutes. That is impossibly slow by every model we had, like finding a spinning top that completes one rotation every hour instead of every second. It should have slowed down and gone dark long ago. The mathematics said it could not still be active. And yet there it was, pulsing, alive, defying the equations. Here is the problem in plain terms. Neutron stars are born spinning fast, really fast, and over time they slow down as they radiate energy. The magnetic field weakens, the pulses fade. Eventually the star crosses what physicists call the death line, the point at which it simply no longer has enough rotational energy to produce the radio emissions we can detect. Once you cross the death line, you go quiet. The physics are clear on this. This object had crossed it. Theoretically, on paper it was dead, and yet the signal kept coming. Slow, rhythmic, undeniable. One explanation researchers are exploring: the star may be feeding off a companion, pulling material from a nearby partner, re-energizing itself, essentially cheating death by borrowing fuel. Another possibility is that our models of magnetic field decay are simply wrong. that under certain conditions, a magnetar can survive far longer than we predicted. Either answer is extraordinary. Either we are missing something fundamental about stellar physics, or we are watching a star do something that has never been documented in the history of astronomy. This discovery matters for reasons beyond one strange star. Every time we find something that breaks our models, we learn more about the actual rules. Not the rules we assumed, but the ones the universe actually runs on. Neutron stars and magnetars are already connected to some of the biggest unsolved questions in physics. Fast radio bursts, mysterious, millisecond-long pulses of radio energy detected from billions of light-years away, may be caused by magnetars. Gravitational waves, the ripples in space-time detected for the first time in 2015, can be produced when neutron stars collide. These objects are not just curiosities. They are windows into the most extreme physics the universe produces. And if a magnetar can survive long past its supposed deathline, if our models are wrong about when and how these objects fade, then we may have been dramatically underestimating how many of them are out there, silent, just beyond the edge of our detection. The universe may be far stranger and far more populated with impossible things than our equations suggest. Astronomers are now actively searching for more of them. New radio telescope arrays, wider sky surveys, more sensitive detectors. The infrastructure for finding these objects is better than it has ever been. Every new confirmed detection rewrites the census of what is out there. And with each one, the picture of the universe becomes a little more honest, a little less tidy, a little more awe-inspiring. Because that is what science actually is. Not a finished map, a constant humbling process of finding out how wrong the last map was. So, what is the rarest type of star scientists just discovered? It is a magnetar, a neutron star with an almost incomprehensibly powerful magnetic field that is somehow still alive, still pulsing, long after every model of stellar physics said it should have gone dark and silent. An object that found a way to keep burning when the mathematics said the flame was out. And that matters. Not just because it is strange, but because every impossible thing we find in space is the universe telling us we still have so much to learn, that the story is not over, that the next discovery, the next object that should not exist, is already out there, waiting. We just have to keep looking. If that kind of question keeps you up at night the way it keeps us up, subscribe. We put out new videos every week on the strangest, most mind-bending corners of the universe. And next time, we are asking a question that sounds simple but turns out to have one of the most unsettling answers in all of physics. What is on the other side of a black hole? See you there.